In this recording, we will start talking about energy. Actually, we'll start talking about the concept of work and energy. Okay. Let's see. Energy probably is one of the physics concepts that is applicable to the most disciplines. It is chemistry is based on energy. Most of the biology is based on energy, and we can think of it in so many different ways. Environmental science, weather, all of those are based on energy. Now, we are all familiar with one of the most fundamental laws of nature, which is the law of conservation of energy, that says that energy can never be created or destroyed. It just changes forms. You can never create or destroy energy. It just changes forms. That's a fundamental law of nature, and that's applicable in all disciplines. Now, energy has many different forms. We know, for example, when you buy gas, you are buying energy. When you are paying your electrical bill, you are paying for energy. When you eat food, you are eating energy. When you exercise, you are spending energy. When you walk, whatever you do, you are going to be spending energy. You rub your hands against each other, and you'll be feeling some other type of energy. Heat is energy. Dropping something from a height, that's an exchange of energy. Climbing, that's another type of energy use. Now, some of the technical terms we use for energy are what we call kinetic energy, or remember the word kinetic means motion, so it's the energy of motion. Whenever energy is going to involve heat, we talk usually of thermal energy. And there is the mass energy. That's the basis of nuclear power plants, but then most importantly, it is the basis of fusion. Let me write the term fusion, which is the process that's responsible for our existence. Fusion of mass in the sun is what produces the energy in the sun that we get here on Earth, and that allows for life to exist on Earth. Without that, we would not exist. So that's another form of energy. Chemical energy, whenever I talked of gas, food that you eat, all of those are chemical energies. Gravitational potential energy, we'll talk more in detail about it later on. That's when someone is going to climb something or go down, there is some changes in gravitational potential energy. Now, there is also what we call electrical potential energy. You know that there is that energy because if you take two charges and put them at proximity of each other, they are going to either repel or attract. The fact that they are going to be able to accelerate just for being there tells you that there is a potential energy there, an electrical potential energy there. Of course, there is a magnetic potential energy as well. The same thing. There is spring potential energy. The word spring might make you think of a coiled spring, but anything that's going to be able to rebound back, that you are going to be able to compress or twist, and then it regaining back its shape, is going to have some type of spring potential energy. For example, a bow and arrow, that's spring potential energy. When you pull on the bow, you are storing spring potential energy for the system of bow and arrow. And when you let go of it, that spring potential energy is going to change into kinetic energy that the arrow is going to acquire and make the trip as it goes out. Now, spring potential energy, anything that, for example, when you have an accident, for example, and a car hits something and then bounces back. That's spring potential energy. Now, we usually, when we talk of energy in physics, one of the things we start up with is the concept of work. Now, work in physics is the act of transfer of energy. It's the process of transferring energy, either into the system or out of the system. It's through work that we make that change of energy from one form to another. Now, in terms of what we will be doing, the concepts of conservation of energy and work, we are going to be able to use them interchangeably with Newton's laws of motion. We are going to be able, and you see most of this chapter is going to include a lot of examples that we are going to be able to solve using energy principles as opposed to kinematic or Newton's laws of motion. Now, what do we define as work? The definition of work in physics is different from the definition of work in general. One key ingredient to work in physics is that you need to have motion. If there is no motion, if there is no displacement, there is no work. That's key. That's important. Now, let's see if I can explain it in terms of this. What if I have, probably I could have had this like this, so a block I'm pulling with a force F. Now that force F is acting both horizontally through this F with the two dashes saying F parallel, so it is acting horizontally and it is acting vertically by pulling that one. Let's call this F with the perpendicular sign. Now, F perpendicularly does not do any work since there is no displacement parallel to that F perpendicular. However, the F parallel is going to be doing work because we have a displacement D parallel to that force F parallel. So actually the work due to the force F is just the work due to F parallel, or F parallel times D. So in other words, whenever we have a force acting on an object to move it a distance D, we look how much of that force is parallel to the displacement. That amount that's parallel to the displacement times the displacement is what work is equal to. Now, and we'll see examples in a little bit. We can use this somewhat interchangeably sometimes. Okay, the unit that we use for work is newtons times meters. And newtons times meters, we call it joules. Remember, newtons is for force, meters is for displacement, so N times meters is equal to joules. So we call that joules. Now, if our force is parallel to the displacement, then you notice that I don't have to worry about F parallel and F perpendicular. The whole F is parallel to the displacement, so my work is just F times D. Okay. The key point here that I'm trying to get across, to do work, you need to have a displacement parallel to the force.